If I asked you to name one person who saved billions of lives, some of you might say Fritz Haber, the guy behind the Haber-Bosch process. It is essential for large-scale agriculture today. In fact, we estimate that half the global population depends directly on it. Pretty impressive, right? If we forget the darker side of the story, you can do your own research. But what if I told you there's someone else, not quite as famous, who hasn't saved billions yet, but probably will? Now, let's ease into the subject. And to be a bit more precise, it's not just one man, but a man, a pig's bladder, and some alcohol. Quite the combo, eh? Now, back in the 18th century, a brilliant French physicist named Jean-Antoine Nollet was curious about how liquids move through membranes. And as a quick reminder, back then, concepts like solutions, solutes, and osmotic pressure weren't well established. His questions were cutting edge for the time. He wanted to see whether membranes could selectively let some liquids through while blocking others. A classic experiment to better understand liquid and membrane behavior. But what he saw was totally unexpected. He added alcohol inside a pig's bladder and immersed it in water, and the bladder inflated until it burst. What he just witnessed was the phenomenon we now call osmosis. Of course, Nollet didn't have the tools we have today, but he figured out that some liquids pass through membranes in only one direction, which means that fluid movement follows certain laws. A pretty sharp conclusion considering the time. Over the years, many scientists like Van 't Hoff, Graham, and Dutrochet helped formalize our understanding of osmosis. Okay, great. But how does that actually work? First, let's go over a few concepts that'll help us understand osmosis. Pressure, put simply, is the force exerted over a certain area. Entropy can be considered as a measure of disorder. This isn't a perfect definition, but it'll do for now. We can express it using the following expression, where delta Q over T stands as the entropic cost. In other words, how much it'll cost in energy to induce the reaction we want. The famous Einstein formula establishes the energy mass equivalence. Gibbs energy is the work that has to be exerted on a system to push it into a certain reaction. Basically, it tells us if a reaction is spontaneous or not. Helmholtz energy is a part of the energy received by the system. This is the part that is convertible into work. These definitions will help us understand osmosis and what equilibrium means. Let's start simple. Imagine a closed system, a mix of compounds that can't exchange matter with the outside world. Everything that changes happens inside the system. So, the system's internal energy changes based on the heat it gains and the work it does, or receives. But real life? We usually deal with open systems, ones that can exchange both energy and matter with their surroundings. In this case, we rewrite the first law using the energy mass equivalence we saw earlier. This last term accounts for the energy coming from mass being added or removed. Basically, every bit of mass that enters or exits carries its own energy. And since each of those bits brings entropy with it, we must also quantify it like this. Putting it all together, we obtain these expressions. And then, by matching these two expressions, we get this. That last term, AI minus T BI, captures how mass transfer affects energy. Think of how each little bit of mass carries its own energy, and therefore by leaving or joining the system, the global energy of the system is affected. As such, they each have the potential to modify the system. We call this the chemical potential, μI. Now we've got the tools to see how systems evolve. A system always moves towards equilibrium, a state where no more spontaneous changes happen. If you have two phases, alpha and beta, for them to be in equilibrium, three conditions must be met. They must reach thermal equilibrium. That means that the variation of entropy is null. No more heat is flowing in the system. They must also reach mechanical equilibrium. That means the variation of Helmholtz energy is also equal to zero, and no net work is needed or generated. And finally, they must reach chemical equilibrium. That means that the chemical potential for alpha and beta are equal. Now let's bring it back to osmosis and that pig's bladder explosion. Imagine this setup. Water on both sides of a semi-permeable membrane. The membrane lets water molecules through, but not solutes like salt. If one side, let's call it phase A, has saltier water, the water molecules have less freedom to move, so they have a lower chemical potential. Therefore, we have mu beta greater than mu alpha. To reach equilibrium, water moves from beta to alpha until both sides are equal, such that mu of beta and mu of alpha are also equal. Now let's bring it back to osmosis and that pig bladder explosion. That water movement creates osmotic pressure. As water keeps flowing in, pressure builds up on one side. If the membrane is rigid, like the pig's bladder, pressure just keeps increasing until it bursts. But wait, how does this help save millions of lives? Yeah, sorry, got a little sidetracked there. Osmosis is everywhere in nature. Just look at cellular respiration, for example. We literally have a motor working thanks to chemiosmosis that helps us to produce energy. But what's really exciting is that we can engineer osmosis to our advantage. That's exactly how millions of people get their drinking water today. We desalinate seawater using reverse osmosis. Engineers apply pressure greater than the osmotic and hydrostatic pressure, forcing water to flow in the opposite direction, leaving the salt behind. And voila! We get clean water. That's huge considering how limited freshwater resources are. This lets us push beyond natural limits. Reverse osmosis is now the most widely used desalination process. And sure, there are others like distillation, but reverse osmosis is by far the most efficient. Since World War II, a lot of work has gone into developing desalination technologies for water treatment. The first ever reverse osmosis plant for desalination opened in 1965 in Coalinga, California. And today, more than 22,000 desalination plants are operating across 150 countries, producing around 110 million cubic meters of drinking water every day. This water is absolutely essential in areas with arid climates, severe water stress, or fast-growing urban populations. Here's how desalination is distributed globally. Other countries use desalination too, but on a smaller scale. In the United States, desalination is mainly used in California and Florida, especially during droughts. In Spain, Europe's leader in desalination, with over 700 small-scale plants, it is used extensively for intensive agriculture in Andalusia and the Canary Islands. And in Australia, facilities in Perth and Melbourne use partial renewable energy. The efficiency of a desalination plant depends a lot on how salty the incoming water is. With standard seawater, which is about 35 grams of salt per liter, a reverse osmosis plant can recover around 40 to 50% as fresh water. But if you're working with brackish water, which is closer to 5 grams per liter, you can get up to 80% or in some cases even more. From an energy standpoint, reverse osmosis plants typically use 3 to 4 kilowatt hours per cubic meter of water, but recent tech advancements have introduced energy recovery devices, which capture the outgoing pressure and reuse it, cutting energy use by up to 50%. Still, desalination is not without its challenges, especially when it comes to the environmental and economic impacts. Unfortunately, desalination has a major downside for marine ecosystems: brine discharge. Brine is the super concentrated salt water left over after we extract the fresh water. It often reaches concentrations of 70 grams per liter, which is twice as salty as seawater. According to a 2023 UN study, for every liter of drinking water produced, about 1.5 liters of brine are generated. That's roughly 150 million cubic meters of brine dumped into the ocean every single day. Here are the main environmental concerns. The first is hypoxia. Brine is denser, so it sinks to the ocean floor, cutting off oxygen and suffocating marine life. The second is temperature. The brine is often up to 10 degrees Celsius warmer than seawater, which disrupts the local thermal balance. And we also have chemical contamination. Brine can carry chlorine, biocides, and heavy metals used in treatment, all of which are toxic to marine organisms. Some regions, like the Persian Gulf, have already seen local salinity levels rise by more than 4 grams per kilogram over the last 20 years. And in some coastal zones, rapid biodiversity loss has been directly linked to desalination plant discharges. At this point, you're probably thinking, why not recycle the brine? Can't we extract salt or recover valuable minerals? Well, it's a bit more complicated than it sounds. In hot, arid countries like those in the Middle East, some brine is used for salt extraction, but that works because of their specific economic and energy situations. Globally, there are a few big barriers. That's why today, over 95% of the world's brine is simply discharged into the sea, completely untreated. We have high extraction costs, especially for valuable elements like lithium or magnesium. There is very much chemical variability as well. Brine composition changes depending on the source water and treatment methods. That means that there's no one-size-fits-all solution, and developing custom setups is expensive. There's also a lack of viable markets. The market for recovered salts is small and local. Combined with weak regulations, most companies just don't have the incentive to invest in reuse systems. From an economic point of view, desalination is actually cost-effective in Gulf countries. Producing 1 cubic meter of drinking water through desalination costs between 50 cents and $1.20 US dollars. Whereas importing that same amount of water from a neighboring country would cost 2 to 4 US dollars. Why? Because countries like the UAE and Saudi Arabia have low energy costs thanks to abundant local energy resources, making desalination more affordable. In contrast, in countries like Japan, desalination is much pricier, costing $3 to $4 per cubic meter. Still, it remains their best option. Japan is an isolated archipelago, and political tensions with China discourage it from importing Chinese water. So, desalination serves as a backup for their natural freshwater supply. In other countries, desalination tends to be used locally in areas hit hardest by drought. Take Spain, for example. Desalination plants are mostly found in 3 regions: Andalusia, the Canary Islands, and the Balearic Islands. And they only serve those specific local needs. We've seen that the cost of desalinated water depends on energy prices and the method used. As mentioned earlier, the 2 main methods are distillation and reverse osmosis. Reverse osmosis costs between 40 and 80 cents per cubic meter. Distillation costs more like 65 cents to $1.80, and it's being phased out worldwide. Still, both are more expensive than treating surface or groundwater, which usually costs 10 to 50 cents per cubic meter. So why don't we just use reverse osmosis everywhere? It's actually quite simple. It's more expensive to build and maintain, and it's a newer technology. Plus, distillation isn't as sensitive to salinity, which made it the go-to method in the Gulf region for a long time. So what's next for desalination? Especially with growing water stress and environmental pressures? The water crisis refers to the widening gap between available resources and rising demand. By 2050, this deficit is expected to multiply by 5. Even with solid water management, demand could outpace supply by 40% in 2030. Now that is a big problem. Under the Paris Agreement, countries are aiming to reduce greenhouse gas emissions. That makes fossil fuel powered desalination unsustainable. That's why several Gulf nations, including the UAE, Saudi Arabia, Oman, and Bahrain, are committing to net zero carbon strategies for 2050 to 2060. These commitments signal a possible double win: reducing emissions and fighting water scarcity. Some countries are already investing heavily. In short, wealthy, water-stressed nations are betting big on desalination. Luckily, desalination is in the middle of a technological revolution. New innovations are emerging that could tackle some of the problems we've talked about. Graphene and carbon nanotube membranes are super efficient and durable. Graphene is a single layer of carbon atoms in a honeycomb structure, like atomic chicken wire. It is only 1 atom thick. It is stronger than steel and highly conductive, and nearly impermeable, unless it is engineered to let water through. We also have renewable energy sources. Some plants are powered by solar, wind, or even wave energy. Additionally, new techniques like reverse electrodialysis or pressure-retarded osmosis are becoming more common and more viable. In Perth, Australia, the desalination plant is powered entirely by wind and supplies 15 to 18% of the city's annual water needs. Saudi Arabia's NEOM project plans a zero-emission mega desalination plant with tech to recover valuable metals from brine. Remember that lithium we talked about earlier? It could be used in batteries, for example. Now, to wrap it all up, desalination is quickly becoming key to global water supply. But its high cost and environmental trade-offs remind us it's not a silver bullet. We'll still need big changes in how we consume and value water to make this planet a healthier place.